Well, now we will talk about the fragmentation mechanism. Is a typical one of the three main functions implemented in the Internet protocol. We need to remember that the MTU, the maximum transmission unit, is the maximum size of the PDUs at the layer 2, at the link layer. And then the IP datagram could be transported via various different technologies that can have different MTUs. Typically, remember that, for instance, the Ethernet technology has an MTU of 1,500 bytes, but other technology could have different MTUs, typically less MTU than 1,500 bytes. Then in those cases, connection across several, the transmission across several different networks could need to pass through, for instance, smaller MTUs than the original network. And in this scenario, the IP version 4 protocol need to implement mechanisms called fragmentation. And for instance, the reassembling will be performed only at the destination host. Then why do we need to fragment? Well, we know that IP supports a maximum datagram size of 64 kbytes. That is, in fact, 64 multiplied by 1024 bytes. That is, in fact, then 65,512 bytes. Then, if we need to, for instance, transmit a datagram, an original datagram larger than, for instance, 1,500 bytes, that is the MTU of Ethernet, we need to perform some kind of fragmentation at the origin in order to send all that information across the network. And finally, at the destination, all those fragments will be reassembled. But across the network, some MTU, some links could have a lower MTU. Then we need to fragment the packets, the datagrams, in order to pass, to transmit the datagram across those links. When is the IP datagram fragmented? It is fragmented when the datagram is longer than the MTU of the network through which the forwarding must be carried out. Who fragments? Fragmentation can occur either in the source host or any intermediate router. Remember this topology where we have, for instance, different MTUs. The fragmentation could occur here, for instance, at the origin, at the source host, or at any of those intermediate systems, that is, routers. Who reassembles? Reassembly of a fragmented datagram is done only at the destination host. The destination host initializes a reassembly timer. If this timer expires before all fragments have been received, it will discard all fragments. And then why this is done in such a way because, for instance, the datagrams could be fragmented, but for instance, use different paths to reach the destination. Then it's not possible to reassemble. Sometimes it's not possible to reassemble all the fragments at the next hop. And the other reason to implement the fragmentation in that way is that the reassembling consume CPU and memory at the routers, at the intermediate systems, and that is something that we need to avoid in order to load to load the routers only the indispensable, the necessary, and not more than that. That's why we don't reassemble at the intermediate routers, but only at the final destination of the datagram. How is the datagram fragmented? The fragmentation process uses some fields of the datagram. One is the offset, another is the more fragment flag of the IP header, and the other is the identifier field. Then the identifier field is used to differentiate fragments of originally different IP datagrams. The offset is used to indicate to the destination host in which order the fragment have to be placed in order to reassemble the original datagram. And the more fragment flag is used to indicate that this is not the last fragment of those datagrams with the same ID. For instance, if a datagram has an offset of zero and more fragment of 0, means that in fact that datagram has not been fragmented nor at the source nor at the any router, intermediate router. If the offset is 0 and more fragment, if the offset is 0, that means that in fact is the first fragment of the original datagram. If the more fragment is 0, that means that this is the last fragment of the original datagram. Then here is typically an example of fragmentation, but in order to understand very well the fragmentation process, we need to understand that all the fragments, any fragment, in fact, is a new datagram. That is, this is the original datagram, for instance, that arrives to a router. The router need to fragment this datagram into fragments, and each fragment, in fact, is a new datagram. Then all the datagrams that are issue of fragmentation process share the same ID field, and only the first fragment has an offset of 0, and typically the last one has the more fragment in 0. Simply in order to clarify, here is not the more fragment, is in fact the end of packet bit. The end of packet bit is a flag that in fact is the inverse of the more fragment flag. But in fact, this is a zero, more fragment 0. This is a more fragment 1. This is a more fragment 0. This is a more fragment 1, more fragment 1, and this more fragment 0. In the case of the offset indicate the first octet of the datagram in which order have to be placed in the reassembly mechanism or process at the destination host. In this example, for instance, host A send a datagram of 1,400 bytes to the host B across this network, where in the middle we have a link of an MTU of 620 bytes. Then why 620 bytes? Because in fact the 20 is used by the IP header. Remember that the IP header typically has the size of 20 bytes. And then here we have the first fragment, that is offset 0, more fragment 1. This is the second fragment. The offset is 600 because the first octet of this datagram is placed in the 600 position and in the reassembly process. And in fact, here we have the last fragment of 200 bytes. That is, in that way, we have a total of 1,400 bytes of payload. And in that case, the offset of the last fragment is 1,200. That is the position of the first octet of this the payload in this datagram. In this case, for instance, we could see a scenario where two routes are possible to reach, for instance, the host B. Then this route, for instance, could perform some kind of load balancing. In that way, for instance, this router could send some datagrams to host B across this route, that is this next hop, and other datagrams designated to host B across this other route, that is the next hop across this other router. This is the explanation that justify why we couldn't reassembly the datagrams in the intermediate systems, because not necessarily the intermediate systems could receive all the fragments designated to the final destination host. Well, finally, the fragmentation process has some disadvantages. One is that the routers need to implement that function, and this causes a negative impact on the data throughput, because it is a CPU and memory consuming task. Although the possibility of fragmentations contribute to the robustness of the IP protocol in difficult network situation because of the disadvantage. It would be better if the sender immediately choose the optimal packet length. Sometimes it's not so simple, but it could be performed by the source host to discover which is the MTU, the optimal packet length, the optimal datagram length to use in order to avoid the fragmentation process at the intermediate routers. That is performed, that could be performed, that discover could be performed using an option called Path MTU Discovery in the internet, supported by the Internet Protocol version 4. But in fact, we will see in the version 6 of the Internet Protocol, we avoid the fragmentation in the routers. We only support the fragmentation in the source host.